The James Webb Space Telescope stands out today as the premier global observatory in space science, carrying a mission that spans the investigation of the deepest enigmas of both our own solar system and distant worlds orbiting remote stars. It seeks to unravel the complex structures of the universe and better understand the role we play within it. In a recent initiative, scientists directed the Webb telescope toward a star located 120 light-years away from our solar system, and what they discovered has sent ripples of excitement and curiosity through the astronomical community. This time, the super telescope revealed compelling evidence for the existence of carbon-based molecules in the atmosphere of a possible ocean world beyond our planet, a revelation that has left many researchers both fascinated and baffled. How is such a surprising finding even possible? This detection provides an intriguing glimpse of a planet that differs significantly from anything found within our own solar system, raising profound questions about the possibility of potentially habitable worlds tucked away in other corners of the vast universe. NASA's James Webb Space Telescope has delivered a groundbreaking discovery regarding the exoplanet K2-18b, which has a mass 8.6 times that of Earth. This finding consists of the identification of carbon compounds, including methane and carbon dioxide, present in the atmosphere of the exoplanet. The Webb telescope's discovery builds on earlier research suggesting that K2-18b might be a planet with characteristics conducive to life, as it appears to possess a hydrogen-rich atmosphere layered over an ocean-covered surface. The first exploration of K2-18b's atmospheric properties was carried out by NASA's Hubble Space Telescope, which transformed our understanding of this distant system and set the stage for more advanced observations. It is important to note that this exoplanet lies approximately 120 light-years away from Earth, located in the constellation Leo, orbiting a cool dwarf star known as K2-18. Positioned within the star's habitable zone, K2-18b belongs to a rare category of planets between the size of Earth and Neptune, a type we do not have within our own solar system, making it particularly intriguing to astronomers. The possibility that K2-18b is an exoplanet with an abundance of carbon and a hydrogen-rich atmosphere excites scientists because some experts believe such worlds may offer ideal conditions for searching for signs of life beyond Earth. The presence of methane and carbon dioxide, combined with the absence of ammonia, supports the theory that this exoplanet could harbor a global ocean beneath a hydrogen-rich atmosphere. Early discoveries regarding this world even raised the possibility of detecting a chemical known as dimethyl sulfide, DMS, a compound that on Earth is only generated by life, with most atmospheric DMS produced by phytoplankton in marine environments. However, the evidence for dimethyl sulfide in K2-18b's atmosphere remains tentative and requires further confirmation. Additional observations from the Global Telescope Network will be essential to verify whether DMS is indeed present at significant levels, as its detection could represent a groundbreaking leap in the search for extraterrestrial life. An astronomer at the University of Cambridge explained that although K2-18b sits comfortably in its star's habitable zone and has shown the presence of carbon compounds, this does not automatically imply that the planet can harbor life as we understand it. The fact that K2-18b has a radius about 2.6 times that of Earth suggests that its core is likely surrounded by an immense high-pressure mantle of ice, somewhat similar to the structure of Neptune. It also possesses a thinner hydrogen-rich atmosphere atop what may be an ocean-covered surface. Although oceans of liquid water are expected on this exoplanet, there is still a possibility that these oceans might be too rigid or otherwise unsuitable to support life. Despite these challenges, researchers have obtained the most detailed spectrum to date of a habitable subneptune, allowing them to identify the molecular composition of its atmosphere with unprecedented clarity. A member of the Cardiff University team elaborated that this achievement was made possible by analyzing the light coming from K2-18b's host star as it passed through the exoplanet's atmosphere. K2-18b is classified as a transiting exoplanet, which means that its observed brightness decreases as it passes in front of its host star. In fact, it was through this method that NASA's K2 mission initially detected K2-18b. This observational approach allows a small portion of the star's light to pass through the exoplanet's atmosphere before reaching space telescopes like Webb, and during these transits, the light carries distinctive signals that astronomers can analyze to estimate the atmospheric gases present. The research team is planning to conduct further investigations using the telescope's mid-infrared spectrograph, which should help confirm their initial findings and provide new insights into the climatic conditions on K2-18b. Their ultimate goal is to search for signs of life on habitable exoplanets, a pursuit that, if successful, could revolutionize our understanding of life's place in the universe. But the James Webb Space Telescope's contributions do not end there. The super-powerful observatory has also made other notable discoveries. Astronomers using Webb have detected complex organic molecules resembling a type of cosmic smoke or smog in a distant galaxy, a finding that marks the earliest known example of such complex organic molecules ever detected by humans. This discovery is not only astonishing but also deeply unsettling, as it challenges and reshapes the very foundations of our cosmological models. These chemicals, technically known as aromatic hydrocarbons, have been identified in a galaxy that formed when the universe was only about 10% of its present age. On Earth, such carbon-based molecules are commonly found in petroleum, coal deposits, and atmospheric pollution like smog. What makes this discovery particularly fascinating is that the molecules detected are not simple compounds like water or carbon dioxide, but are instead large, complex structures with dozens or even hundreds of atoms. It is remarkable to consider that the universe was capable of assembling such large and complex molecules so soon after the Big Bang, defying long-standing expectations based on our existing cosmological models. To put this in perspective, the light detected by astronomers from this early galaxy began its journey less than 1.5 billion years after the Big Bang, while the universe itself is currently estimated to be about 13.8 billion years old. This means we are observing the very earliest steps in the evolution of the cosmos as we know it today. What is even more impressive is that this detection was made possible only because of the extraordinary capabilities of the James Webb Space Telescope, which will allow scientists to continue making such observations for almost a billion more years into the past. One can only wonder if we could look even further back in time, could we find more of these molecules even closer to the birth of the universe itself? This tantalizing possibility raises fundamental questions about our scientific assumptions and the accuracy of our current cosmological framework. Until now, previous efforts to detect complex organic molecules in ancient galaxies could only confirm whether or not the chemicals were present in general. But with Webb's unmatched resolution, astronomers can now observe the fine details of where these molecules are located within their galactic environments. Furthermore, the non-uniform presence of these molecules in the early galaxy, known as SBT 0418-47, has yet to be fully explained, adding another layer of mystery. Perhaps the most striking aspect of this discovery is that the galaxy itself was already as massive as our own Milky Way, and that its stars have produced as much carbon and oxygen as the stars of our galaxy, despite being only 1/10 the Milky Way's current age. As humanity ventures deeper into the unknown, armed with knowledge, technology, and a relentless curiosity, we are constantly humbled by the vastness and complexity of the cosmos. Each new scientific breakthrough, whether it is the detection of carbon-based molecules in the atmosphere of a potentially habitable exoplanet or the identification of complex organic chemicals in ancient galaxies, brings us one step closer to unraveling the profound mysteries hidden among the stars. With each success, our cosmic exploration network advances, and it seems only a matter of time before the universe reveals new secrets and shines with renewed light, inviting us to expand the boundaries of our understanding and to continue asking the questions that have driven human wonder for millennia. Are you curious what we will discover next? The James Webb Space Telescope has reshaped not just how we look at the sky, but how we see ourselves in the universe. With every observation it sends back to Earth, it forces scientists and astronomers to confront new possibilities and rethink old assumptions. Recently, the Webb telescope directed its gaze toward a star system 120 light-years away, uncovering tantalizing evidence of carbon-based molecules in the atmosphere of an exoplanet that may very well be an ocean world. This finding has reverberated through the scientific community, shaking the foundations of what we believed about life-bearing environments beyond Earth. How is it possible that such a discovery was made? The Webb telescope's mission is nothing short of monumental: to study both the familiar and the unknown, from the planets within our own solar system to the distant, faint worlds circling stars we can barely see. By examining the atmospheric makeup of exoplanets, scientists hope to understand not only their physical properties, but also whether they might offer the right conditions for life. This latest finding is a captivating glimpse into a planet very different from anything in our solar system and raises profound questions about what kinds of worlds might be out there waiting to be discovered. The exoplanet at the center of this discovery is K2-18b, a super-Earth with a mass roughly 8.6 times that of our planet. Located in the constellation Leo, it orbits a cool dwarf star called K2-18, right in the star's habitable zone where conditions might allow liquid water to exist. What makes K2-18b especially intriguing is its size. Planets between the size of Earth and Neptune are rare in our solar system, which makes it hard to compare them to anything nearby. Scientists were able to detect the presence of carbon compounds, particularly methane and carbon dioxide, in its atmosphere, which hints at a hydrogen-rich layer surrounding what might be a water-covered surface. Early atmospheric studies using the Hubble Space Telescope had already transformed our understanding of the system, but Webb's far more sensitive instruments have now provided the most detailed spectral data yet, confirming the molecular makeup of this alien world. Some astronomers have even suggested the possible presence of dimethyl sulfide, a molecule on Earth that is almost exclusively produced by marine life like phytoplankton. Although this particular finding needs further confirmation, the mere suggestion that such a biosignature might be detectable has sent ripples of excitement across the scientific community. However, scientists remain cautious. As an astronomer from the University of Cambridge explained, just because K2-18b is in a habitable zone and has carbon-based molecules doesn't mean it harbors life. Its radius, about 2.6 times that of Earth, indicates that it likely has a thick, high-pressure mantle of ice much like Neptune, with a thinner hydrogen-rich atmosphere above. While there may indeed be liquid oceans, they might be subject to extreme pressures or conditions that make them inhospitable to life as we understand it. Yet the fact that researchers were able to capture such detailed data by analyzing the starlight passing through K2-18b's atmosphere marks a major technological achievement. This exoplanet is what's known as a transiting world, meaning its brightness dips slightly each time it passes in front of its star from our vantage point. By studying how the host star's light filters through the exoplanet's atmosphere during these transits, astronomers can infer which gases are present. The Webb telescope's capabilities have allowed for unprecedented detail, and upcoming observations using its mid-infrared spectrograph are expected to shed even more light on K2-18b's climate, atmospheric chemistry, and perhaps its true potential for life. But the James Webb Space Telescope's breakthroughs don't end there. In another groundbreaking observation, astronomers using Webb have detected complex organic molecules in a distant galaxy, molecules similar to those that create smoke or smog here on Earth. This discovery marks the earliest known detection of such complex carbon-based molecules in the universe and challenges our understanding of how quickly organic complexity arose after the Big Bang. Specifically, these molecules, called aromatic hydrocarbons, are found in familiar substances on Earth like petroleum and coal, as well as in pollution-heavy smog. What makes this observation remarkable is that we are not talking about simple compounds like carbon monoxide or water, but large molecular structures made of dozens or even hundreds of atoms. That such molecular complexity emerged so soon, just 1.5 billion years after the Big Bang, when the universe was only about 10% of its current age, is astonishing and forces cosmologists to rethink models of chemical evolution. To put this into perspective, the light we see from this distant galaxy began its journey across the universe when the cosmos was young and still settling into its current shape. The galaxy, known as SBT 0418-47, is already as massive as the Milky Way and has generated just as much carbon and oxygen, despite being much younger. This raises compelling questions. How did such complex organic chemistry emerge so rapidly? Could it be that the universe, even in its earliest stages, was chemically fertile enough to set the stage for life? Prior to Webb, astronomers had attempted to detect such complex molecules in ancient galaxies, but the resolution was too limited to offer anything more than a binary yes or no signal. Now, thanks to Webb's sensitivity, scientists can pinpoint where these molecules are located within early galaxies and begin to study their distribution and role in cosmic evolution. The patchy, non-uniform presence of these organic compounds still puzzles researchers, and their origin remains a mystery. But what is clear is that the cosmos was capable of producing sophisticated chemistry much earlier than previously thought. With each passing discovery, the James Webb Space Telescope reminds humanity just how small we are in the grand tapestry of the universe. Every new data set deepens our understanding and simultaneously expands the frontier of what we do not yet know. The detection of carbon-rich atmospheres on distant exoplanets and the identification of ancient aromatic hydrocarbons in young galaxies both suggest that the universe may be teeming with the raw materials for life. Whether those materials have in fact given rise to life elsewhere remains one of the greatest questions of our time. Yet, armed with tools like the Webb telescope, we are now closer than ever to finding out. In many ways, each scientific breakthrough Webb delivers is not just a discovery but an invitation, a call to continue exploring, questioning, and seeking. The vastness and complexity of the cosmos humbles us, reminding us that even with all our advances, we are only beginning to scratch the surface of the universe's deepest mysteries. Looking ahead, the research teams working with Webb are determined to push even further, using every capability of the telescope to investigate not just K2-18b, but a wide range of exoplanets, stars, galaxies, and cosmic phenomena. Their ultimate goal is bold: to find definitive signs of life beyond Earth. Such a discovery would not only transform planetary science but would fundamentally alter our understanding of our place in the universe. If life exists elsewhere, it would imply that biology might be a common cosmic occurrence rather than a rare earthbound phenomenon. It would force us to rethink everything from the origins of life to the future of human civilization. But even if life remains elusive, the journey of discovery itself holds immense value. Every new observation, every surprising result helps refine our theories and sharpens the questions we ask. At the heart of this exploration is a profound sense of wonder. Humanity's curiosity about the stars is as old as our species, and today, with the help of cutting-edge technology, we are finally equipped to seek answers in a meaningful way. The James Webb Space Telescope stands as a testament to what can be achieved when nations, scientists, and engineers come together to pursue a shared vision of discovery. Its accomplishments thus far, from revealing the atmospheric composition of distant ocean worlds to detecting ancient organic molecules in the farthest reaches of the cosmos, hint at even greater revelations to come. As we stand on the brink of a new era of cosmic exploration, we are reminded that the universe is not a static backdrop, but a dynamic, evolving landscape filled with secrets waiting to be uncovered. In the end, the Webb telescope's discoveries are about more than data, they are about meaning. They challenge us to reflect on the nature of existence, the origins of life, and the future of our species. They remind us that despite our technological prowess, we remain tiny beings in a vast and ancient cosmos. Yet armed with knowledge and driven by curiosity, we are determined to reach out, to explore, and to understand. With every observation, we take another step on a journey that spans light years and eons, moving closer to answers that have eluded humanity for millennia. As the Webb telescope continues to peer deeper into space and further back in time, one thing is certain: the universe still holds countless surprises, and it is only a matter of time before it reveals even more of its astonishing secrets. As the James Webb Space Telescope continues its groundbreaking mission, the scientific community is preparing for an even more ambitious phase of exploration. Over the next several years, researchers plan to use Webb's powerful instruments to investigate dozens of exoplanets, including smaller rocky worlds more similar to Earth. While K2-18b has offered a tantalizing glimpse of a hydrogen-rich ocean planet, astronomers are eager to examine planets in systems like TRAPPIST-1, where multiple Earth-sized worlds orbit a cool red dwarf star just 40 light-years away. Webb's ability to perform transmission spectroscopy, analyzing the starlight that filters through a planet's atmosphere during transits, makes it ideally suited to search for biosignatures such as oxygen, ozone, methane, or combinations of gases that, on Earth, point strongly to biological activity. For the first time in human history, we have a real chance to look for life not just in our own backyard like Mars or Europa, but on worlds orbiting distant stars.